Okay, let's now investigate a special situation that we may encounter when evaluating some integrals. Suppose that I would like to evaluate the following integral, the integral of 1 over 2x dx. And as you see, this is a simple integral. But I would like to investigate the value of that integral using two methods. First, by using the rule that states that the integral of 1 over a plus bx dx equals to the natural logarithm of the absolute value of a plus bx, the linear denominator, divided all by the coefficient of x, which is b in that case. Of course, plus the constant of integration, c. And the second rule I'm going to use is the rule that allows you to, or the property that allows you to take the constant out of the integral. That is, the integral of 1 over, let's say just bx without a in the denominator, just bx dx. We know that this must evaluate to the same value as the 1 over b times the integral of 1 over x dx. Let's say that this is the second property that we are going to rely upon evaluating this integral there. Okay, I'm going to use the first method, then the second method, and see what this special situation that we may encounter. Okay, I'm going to write the same integral that is written above, 1 over 2x dx, but using or relying upon the first rule there. We see that the 1 over a plus bx resembles 1 over 2x, except that a is equal to 0. So this is just 1 over 2x plus 0, or 0 plus 2x. So the a there is the 0 there, and the b above is the 2 below. Great. So according to this rule here, we may say that this integral evaluates to the natural logarithm of the absolute value of 2x plus 0 divided by the coefficient of x, which is 2, plus c, or simply just the natural logarithm of absolute 2x over 2 plus c. This is our first answer. Okay, you may say that this is easy. Yes, it is, but let's investigate what we are going to get when we use the second approach. That is this rule here. Okay, let's write the integral again. We want to integrate 1 over 2x. But depending on that rule here, that rule there, we may take 1 over b out. And 1 over b in this case is just 1 over 2. So we may write this as 1 over 2 times the integral of 1 over x dx. Okay, and using the simplest version of this rule here, when a equals 0 and b equals 1, we have got that this integral there just evaluates to 1 over 2 times the natural logarithm of absolute x over 1, where 1 is the coefficient of x, plus c. Okay, to differentiate between these two c's, I'm going to just call this second c star, just a second constant. And as you see, we may simplify this as 1 times ln, so it's just ln of x over 2 times 1 is just 2, plus c star. And this is the answer for the same integral that we evaluated there. Take a moment just to look at both answers there that are for the same integral. This integral there is the same as that integral there, but look at the answers. What do you see there? Of course, you may have noticed that although they are answers for the same integral, the integral above contains 2 inside the ln, but this integral that does not contain that 2. There is no 2 here. So you may say, how come we have integrated the same quantity and getting different answers. And let's show that these answers are actually the same. So I'm gonna write the answers below and show that they are the same answer. Okay, so the first answer that we got above is just the len of 2x over 2 plus c, and we want to show that this is the same, not equal to, but the same as len absolute x over 2 plus c star. So let's show that they are identical, but not equal in the numerical meaning, and I'm going to clarify what does that mean. So I'm going to reach the result by proving that this is identical to that. That is, I'm going to start from the above integral. So the above integral is the len of 2x over 2 plus c. And of course, as you know from the basic rules of logarithms, we may write this as the len of 2 times absolute of x, all of that contained in some big parentheses there. So since 2 is positive, I can take it out of the absolute value without any worry. And according to the rules of logarithms, also I can turn this product into plus when both of these are positives. Of course, we are speaking about the rule that applies in real analysis. We're not including complex analysis there. So, of course, all of that over 2 plus c. And according to the rule mentioned a little while ago, this is len of 2 plus len of absolute x, all of that over 2 plus c. Notice that all of these are constants. This is a constant and this is a constant, so we can just write this as, we can split this one fraction into two fractions, so this becomes the len of 2 over 2 plus len of absolute x over 2 plus c. Combining this and that constant, we can get len absolute x over 2 plus len of 2 over 2 plus c. And this is all just one constant. Some constant c plus len 2 over 2 is just a new constant that we may call, for example, c sub 1. And this evaluates to len of absolute x over 2 plus c sub 1, which is some unknown arbitrary constant. And this is another form of that answer, which contained 2 at the beginning, which is identical to the answer that we got using the other method. So len absolute x over 2 plus c1 is the same as that answer here, which is the same as this answer there that we wanted to show. So this is the same as len absolute x over 2 plus c star. This is the same as len absolute x over 2 plus c star, which we got from the second method. And this one is the same as the one that we got from the first method. And they are identically the same, except that c1 is different generally from c star because these constants depend on the initial or boundary conditions. So what we may say here is that they are identical answers, although the constants appear not to be so. But as I said, these constants depend on the initial conditions. So this is how we prove that they are actually the same integral. So if the same initial conditions are associated with both integrals, then these constants will be identical. So these will be identical if the initial conditions associated with both integrals are the same. So, okay, let's speak about a special collection of integrals that we may encounter similar situations with. They are the trigonometric or the integrals of trigonometric quantities. For example, if you would like to integrate the sine of 2x dx, you may say that this is equal to, according to the simple rule, negative cosine of 2x all over 2 plus some constant c. But we may also write this integral here as the integral of, according to the most common double angle formulae, this is just the double of sine of x cosine of x dx, and we can use the integration by substitution to write, okay, let's suppose that u is just the sine of x, so du is just cosine of x dx, and finally dx is just du over cosine of x, the simple method of integration by substitution. So this becomes the integral of 2 sine is just now u cosine of x, dx is just du over cosine of x, so now they cancel, the cosines cancel, and we are integrating just 2u du, which evaluates to u squared plus c, but u is just sine, so this is just sine squared of x plus c. And again, how come we are getting the two answers that are different, apparently different, for the same integral? This integral here is sine squared of x plus c, but that one there is negative cosine 2x over 2 plus c. Both integrals, or both answers, are for the integral of the same quantity, sine 2x, so they're apparently different, but actually they're the same. And we're going to show this using this similar process that we used for the integral above, for the case above. So the second one here is just sine squared. Let's call this c star, second constant, sine squared of x plus c star. And the first one that we got was the negative cosine 2x over 2. Negative cosine of 2x over 2 plus c. I'm going to turn this into that. Okay, you are seeing here sine squared, and you may think that the best way is to get rid of the square, because there is no square here, which is the correct way. Sine squared, according to a well-known identity, is just equal to, this is just equal to half of 1 minus cosine of 2x, of course, plus that c star here, here. And as you see, we are actually done. Just evaluate the half inside. You're getting half minus half cosine of 2x plus c star, and let this be the first term. Combine the half with the c star. This half, isolated half with the c star, this evaluates to 1/2 cosine of 2x plus c star plus half, which is again just one constant that we may call c1, for example. So this is just equal to now negative half cosine of 2x plus c sub 1, which has the same form as that one there, c1 instead of c. We explained why this may be, why these concepts may be different. And that's it. You may encounter this problem, this apparent, which appears to be a problem in many trigonometric integrals or integrals of trigonometric functions, and always the way to show that the answers of the same integral with two different methods are identical is to use trigonometric identities that will turn the answers to be, or turn one of the answers to be identical to the other. And that's it.